Imagine for a moment that you are walking through the house you grew up in. Every floorboard has a familiar creak, every hallway a memory, and every door leads exactly where you expect it to. You know this place. You've lived here your entire life. You know the way the light hits the kitchen table at 4 in the afternoon, and you know the exact sound the front door makes when it latches shut. You could navigate it blindfolded, a perfect mental map etched into your very being. But one afternoon, as you reach for the handle of the closet in the hallway, the one that has always held nothing but old coats, dusty boxes, and perhaps a forgotten umbrella, you open it, and instead of the familiar musty scent of forgotten things, you find yourself standing on the edge of a vast, sun-drenched meadow that stretches for miles under an alien sky. The walls of your house are still behind you, solid and real, but the world in front of you is something entirely different, something impossible. It's a place that shouldn't exist, yet there it is, solid and real under your feet. A breathtaking, terrifying vista that defies all logic. This is not a dream, nor a fantasy. This is the feeling currently rippling through the most brilliant minds in the world of astrophysics. For decades, we thought we knew our cosmic home. We had the blueprints, the measurements, and the mathematical laws that governed every star and galaxy, every whisper of gravity, every burst of light. But recently, the James Webb Space Telescope, the most powerful eye we have ever turned toward the heavens, a technological marvel orbiting 1 million miles from Earth, opened a door we thought we understood, only to reveal a universe that doesn't match our maps, a reality that is fundamentally at odds with our most cherished theories. In the quiet, almost monastic halls of Johns Hopkins University, a man named Adam Riess sits with a set of numbers that shouldn't be possible. Riess is not just any scientist. He is a titan in his field, a Nobel Prize winner, a man whose groundbreaking work helped us discover that the universe is not just expanding, but accelerating, pushing galaxies apart at an ever-increasing speed. He has spent his life meticulously measuring the heartbeat of the cosmos, tracking the light of distant stars with a precision that was once thought impossible, pushing the boundaries of human knowledge. But now, he is issuing a warning that is as profound as it is unsettling, a statement that echoes with the weight of cosmic implications. He says, quite simply, that we have misunderstood the universe. The data coming back from James Webb isn't just a minor error, a statistical anomaly, or a blurry image that needs sharper focus. It is a fundamental contradiction, a deep-seated paradox that strikes at the very core of our cosmic understanding. It suggests that the universe we've been studying for a century, the one described in our textbooks, calculated by our greatest minds, and confirmed by countless observations, might not be the universe we actually live in. If you find yourself captivated by these profound mysteries of the deep cosmos, by the thrill of discovery and the unsettling beauty of the unknown, I invite you to join our journey by liking this video. It helps us continue to explore these silent, distant frontiers together, bringing these cosmic revelations to a wider audience. We are standing at a crossroads where our most cherished theories are beginning to crumble, where the very fabric of our cosmic understanding is fraying at the edges. And what lies on the other side is a reality far stranger, far more complex, and infinitely more fascinating than we ever dared to imagine. This isn't just a story about telescopes and abstract mathematics. It's a deeply human story about the limits of our knowledge, the relentless pursuit of truth, and the humbling moment we realized that the vast, dark ocean of the cosmos still holds secrets that could rewrite everything we know about existence itself. For over 100 years, humanity has been building a standard model of the universe, a grand intellectual edifice known as Lambda CDM. It's our master blueprint, a comprehensive set of equations and principles that tells us how the Big Bang happened, how gravity pulls matter together to form stars and galaxies, and how dark energy pushes it apart, accelerating the universe's expansion. For a long time, this model worked beautifully, explaining almost every observation with remarkable accuracy. It predicted the background glow of the Big Bang with incredible precision. It explained the way galaxies cluster together like cosmic cobwebs, forming the large-scale structure of the universe. We felt a sense of profound intellectual security within its framework, believing that we had finally decoded the master plan of existence, that the universe was, at last, comprehensible. But science, in its very nature, has a way of humbling us just when we think we've mastered it, of revealing new layers of complexity just when we believe we've reached the final frontier of understanding. Think of the expansion of the universe like a massive, invisible river flowing silently through the void. Everything in the cosmos, every star, every galaxy, every atom, every particle of light is being carried along by this inexorable flow. If we want to know the history of the river, to understand its speed and its currents, we have two primary ways to measure it. We can look at the very beginning, near the source, at the moment the river first began to flow, and calculate how fast the water should be moving by the time it reaches us today. Or we can stand right here on the bank in the present moment and measure the speed of the water as it rushes past. In a perfect, predictable world, these two measurements should match perfectly, yielding the same velocity. But in our universe, they don't. The source measurement, derived from the faint echoes of the Big Bang, tells us the river is flowing at one speed, approximately 67 kilometers per second per megaparsec, while our local measurement, taken from the stars and galaxies closest to us, tells us it's moving significantly faster at about 73 kilometers per second per megaparsec. This gap, this persistent 8% difference, is what scientists call the Hubble Tension. It sounds small, a mere numerical discrepancy, but in the world of precision physics, it's the equivalent of a bridge being built from two sides and meeting in the middle, only to find the two halves are missing each other by 50 feet. A catastrophic misalignment that renders the entire structure unusable. It means something is fundamentally, profoundly wrong with our understanding of the river itself, or perhaps with the very laws that govern its flow. For years, many scientists hoped this was just a mistake, a subtle error in measurement, a calibration issue, or an observational bias that would eventually be ironed out with better data. They thought our local measurements were being blurred by the limitations of our telescopes, obscured by cosmic dust, or distorted by the complexities of stellar populations. They waited for James Webb, believing its crystal clear infrared vision, its unprecedented sensitivity, and its ability to cut through the cosmic fog would finally show us that the two numbers actually do match, that the universe was, after all, behaving as expected. But when the first data came back, the silence in the scientific community was deafening. quickly followed by a wave of stunned realization. James Webb didn't fix the mistake. It didn't resolve the tension. It confirmed that there is no mistake in the measurements. The two numbers are both right, derived from impeccable observations, and yet they are different. This is the moment the tension became a crisis. It's the moment we realized that the universe we see through our telescopes, the universe we inhabit, is not the universe our theories predicted. We are living in a reality that defies its own laws, a cosmic enigma that challenges our deepest assumptions, and today we are going to find out why. As we move forward, the focus is shifting from, is there a mistake, to what are we missing? The crisis is no longer about the numbers, it's about the physics. We are entering a new era of discovery, one where we have to be willing to throw away our old maps and start from scratch. James Webb has shown us that the universe is not the simple, elegant machine we thought it was. It is a place of deep mystery, a place where the laws of physics themselves might be evolving. We are like sailors who have reached the edge of the known world and found that the ocean doesn't end. It just becomes deeper and more dangerous. The judge has failed to bring us back to the safety of our old theories, and now we are left to navigate the unknown on our own, armed with new data and a renewed sense of wonder at the cosmic enigma that surrounds us. The elegant simplicity of our model is giving way to a bewildering reality, forcing us to question everything we thought we knew about the cosmos and our place within it. The stage is set for a scientific revolution, one that promises to redefine our understanding of existence itself. To understand the magnitude of the crisis we find ourselves in, we must first look at the masterpiece of human thought that is currently under threat. For decades, scientists have relied on what they call the Standard Model of Cosmology, or Lambda C DA M. It is the most successful theory in the history of science for describing the large-scale structure of the universe. Think of it as a massive, intricate cathedral, built over a century by thousands of architects, each adding a stone, a window, or a spire. Every piece of this cathedral was designed to fit perfectly with the others, guided by a single, elegant blueprint. This blueprint tells us that the universe began in a hot, dense state we call the Big Bang, and that it has been expanding ever since, shaped by the invisible hands of dark matter and dark energy. For a long time, this cathedral stood as a testament to human reason. It explained almost everything we saw in the night sky, from the way galaxies clustered together like cosmic cobwebs to the way light from distant stars is stretched as it travels through expanding space. We felt a sense of profound security within its walls, believing that we had finally decoded the master plan of existence. But there is a catch to building such a perfect structure. In a cathedral where every stone depends on the one beneath it, even a single crack in the foundation can threaten the entire edifice. And that is exactly what is happening now. The Standard Model isn't just a collection of ideas. It's a mathematical framework that allows us to predict the future and reconstruct the past. If we know the conditions of the universe shortly after the Big Bang, the model tells us exactly how it should look today. It's like having a photograph of a seedling and using the laws of biology to predict exactly how the fully grown oak tree will look 50 years later. For a long time, the tree we saw through our telescopes looked exactly like the one the seedling predicted. We were confident. We were certain. We were perhaps a bit too comfortable in our beautiful illusion. The Standard Model, at its heart, is built upon a few fundamental pillars. First, there is the Big Bang Theory, which describes the universe's origin from an extremely hot, dense state. This isn't just a philosophical idea. It's supported by a wealth of observational evidence, including the expansion of the universe itself, first observed by Edwin Hubble in the late 1920s. Hubble's groundbreaking discovery that galaxies are receding from us and that the farther away they are, the faster they recede, provided the initial empirical bedrock for the idea of an expanding universe. This expansion, when traced backward in time, inevitably leads to a point of immense density and temperature, the Big Bang. Further evidence came from the abundance of light elements like hydrogen and helium. The Big Bang model accurately predicts the observed cosmic ratios of these elements, forged in the universe's first few minutes, when the entire cosmos was a nuclear furnace. And most crucially, there is the cosmic microwave background, CMB, which we will delve into shortly. These three pillars, working in concert, paint a consistent and compelling picture of our universe's fiery birth and subsequent evolution, a cosmic saga spanning billions of years. Second, the model incorporates the existence of dark matter. Imagine trying to weigh a room full of people, but you can only see a few of them. You know there are more people there because the room is heavier than it should be, based on who you can see. That's dark matter. It's an invisible, mysterious substance that doesn't interact with light or other forms of electromagnetic radiation, making it utterly transparent to our telescopes. Yet, its gravitational pull is immense and essential to explain how galaxies spin at rates that would otherwise tear them apart, and how they cluster together into the vast cosmic web we observe. Without dark matter, the visible matter in galaxies simply doesn't have enough gravitational heft to hold itself together. It acts as the cosmic scaffolding upon which the visible universe is built, holding everything in place, a silent, unseen architect of cosmic structure. Its presence was first inferred by Fritz Zwicky in the 1930s, observing the anomalous velocities of galaxies in the Coma cluster, a finding so bizarre at the time that it was largely dismissed. Decades later, Vera Rubin's meticulous work on galaxy rotation curves in the 1970s provided compelling evidence. The outer stars of galaxies were orbiting far too fast to be held by the visible matter alone, implying a massive, unseen halo of dark matter. Despite decades of searching, its fundamental nature remains one of the greatest unsolved mysteries in physics, a phantom presence that shapes the cosmos. Then there is dark energy, an even more enigmatic component. If dark matter is the invisible glue that holds structures together, dark energy is the invisible force pushing everything apart, accelerating the universe's expansion. For most of cosmic history, gravity was the dominant force, slowing down the expansion of the universe after the initial Big Bang, much like a ball thrown upwards gradually slows before falling back down. But about 5 billion years ago, something shifted dramatically. The expansion began to accelerate, defying gravity's pull. It was as if the universe hit the gas pedal and has been speeding up ever since, destined to eventually stretch galaxies so far apart that they will disappear beyond our cosmic horizon, leaving us in an isolated, empty void. This acceleration is attributed to dark energy, a mysterious pressure inherent to space itself, a property of the vacuum that acts as a repulsive gravitational force. It's the reason why distant galaxies are not just moving away from us, but are speeding up as they go. The discovery of this accelerating expansion in the late 1990s, which earned Adam Riess and his colleagues the Nobel Prize, was a monumental shock to the scientific community, forcing us to fundamentally revise our understanding of the universe's ultimate fate. Together, dark matter and dark energy make up about 95% of the universe's mass energy content, with the ordinary matter that makes up stars, planets, and us accounting for a mere 5%. The lambda CDM model, with its elegant inclusion of these dark components, weaves them together into a coherent narrative of cosmic evolution, from the first moments of the Big Bang to the present day. A narrative that has, until recently, stood as our most complete and satisfying picture of reality. The most powerful piece of evidence for this model, and the source of one side of our current cosmic crisis, came from a mission called Planck. Launched by the European Space Agency, the Planck satellite was designed to capture the oldest light in the universe, the cosmic microwave background, or CMB. This light is the afterglow of the Big Bang, a faint hum of energy that has been traveling through space for over 13 billion years. It is, quite literally, a baby picture of the cosmos, taken when the universe was only 380,000 years old. At this incredibly early stage, the universe was a hot, dense plasma, a swirling soup of protons, electrons, and photons, too opaque for light to travel freely. Any photon would quickly scatter off an electron, making the universe a foggy, impenetrable haze. But as it expanded and cooled, reaching a temperature of about 3000 Kelvin, electrons and protons finally combined to form neutral hydrogen atoms. Suddenly, the universe became transparent, and the photons, the ancient light of creation, were free to stream across space. The light from that moment, stretched and cooled by billions of years of expansion to a mere 2.7 Kelvin, is what we detect as the CMB today. It's a fossilized imprint of the early universe, a cosmic Rosetta Stone, carrying information about the universe's initial conditions and its fundamental parameters. When scientists analyzed this picture, they found something extraordinary. The CMB is not perfectly uniform. It contains tiny temperature fluctuations, only a few parts in 100,000. These minute anisotropies, or variations, are not random noise. They are the imprints of quantum fluctuations in the very early universe, magnified by a period of rapid expansion known as inflation, that eventually grew into the seeds from which all the galaxies and structures in the universe eventually grew. These cosmic fingerprints, these subtle variations in temperature, are the echoes of creation, providing a direct window into the universe's infancy. By plugging these patterns into their equations, cosmologists could calculate the expansion rate of the universe with incredible precision. The number they got, derived from this pristine snapshot of the early cosmos, was approximately 67 kilometers per second per megaparsec. This means that for every 3.26 million light-years you move away from Earth, space is expanding by 67 kilometers every single second. It was a triumph. The blueprint worked. The cathedral was solid. The CMB data not only confirmed the Big Bang, but also provided precise values for the universe's age, composition, and geometry, solidifying the lambda CDM model as the reigning paradigm of cosmology, a testament to humanity's ability to understand the grandest scales of existence. But then, we decided to check the measurement another way. Instead of looking at the seedling and predicting the tree, we decided to measure the tree directly. We looked at the stars and galaxies in our own cosmic backyard, the ones that are relatively close to us in the present day. This is where the trouble began. When astronomers like Adam Riess used the cosmic distance ladder to measure the expansion rate of the local universe, they didn't get 67. They got 73. At first, many thought this was just a measurement error. After all, measuring the distance to a star millions of light years away is incredibly difficult. It's like trying to judge the distance of a candle flickering in a dark forest from miles away. You might be off by a few feet, or even a few yards, but as the measurements became more precise, the gap didn't disappear. It grew. The 67 from the early universe and the 73 from the modern universe refused to meet. This 8% difference might seem small, but in the world of precision cosmology, it is a chasm. It's the difference between a universe that is 13.8 billion years old and one that is significantly younger. It's the difference between a universe that behaves according to our laws and one that is doing something we don't understand. If the 67 is right, then our local measurements must be wrong. But if the 73 is right, then our baby picture of the universe is telling us a story that doesn't lead to the world we see today. It means the seedling grew into a different kind of tree than the laws of biology predicted. It means the blueprint for our cathedral is flawed. And if the blueprint is flawed, then the entire structure, the Big Bang, dark matter, dark energy, the very history of time itself, might be built on a foundation that doesn't actually exist. This is the Hubble Tension, and for years it has been the ghost haunting the halls of physics. It is a quiet, persistent reminder that our beautiful illusion might be just that, an illusion. We have spent a century building a map of the cosmos, only to find that the territory doesn't match the paper. We are like explorers who have spent years charting a continent, only to reach the coast and find that the ocean is where the mountains should be. The standard model, for all its beauty and success, is failing its most important test. It cannot reconcile the past with the present. It cannot explain why the universe is expanding faster than it should be. And as we turn our gaze towards the even more distant past with the James Webb Space Telescope, we are finding that the cracks in our cathedral are not just in the foundation, they are everywhere. The very fabric of our cosmic understanding is fraying at the edges, revealing a universe far more complex and perhaps far more alien than we ever dared to imagine. The elegant simplicity of our model is giving way to a bewildering reality, forcing us to question everything we thought we knew about the cosmos and our place within it. The stage is set for a scientific revolution, one that promises to redefine our understanding of existence itself. To understand why the number 73 is so certain, why it stands as an unyielding testament to a cosmic anomaly, we have to delve into the intricate science of how we measure the distance to the stars. It is a process known as the cosmic distance ladder, a meticulously constructed edifice of astronomical measurement, where each rung depends critically on the accuracy and precision of the one below it. Imagine you are standing on a long, straight road at night, stretching endlessly into the darkness. In the far distance, you see a single streetlight, a tiny beacon against the inky blackness. You want to know how far away it is. If you know exactly how bright that light is at its source, say, a standard 100-watt bulb. You can measure how dim it looks from where you are standing and, through a simple calculation, determine its distance. This is the basic, elegant principle of a standard candle in astronomy, an object whose intrinsic brightness is known. But there's a fundamental problem. How do you know for sure it's a 100-watt bulb? You have to walk up to it and check, or at least have a reliable way to verify its true luminosity. But in the vast, cold vacuum of space, we can't simply walk to the stars. So, we have to build this ladder, step by painstaking step, where each rung provides the calibration for the next, allowing us to reach ever greater cosmic distances. The first, most fundamental rung of this ladder is parallax. Parallax is a concept we experience every day without even realizing it. A trick of perspective that our brains constantly compute. Hold your finger out at arm's length and alternate closing your left and right eye. Your finger appears to shift against the background. The closer your finger, the more pronounced the shift. Astronomers use this exact principle, but on a cosmic scale, to measure the distance to nearby stars. As the Earth orbits the Sun, our vantage point in space continuously changes. Over 6 months, the Earth moves from one side of its orbit to the other, creating a colossal baseline of nearly 300 million kilometers, the diameter of Earth's orbit. By observing a star from these two diametrically opposed points in our orbit, we can see it appear to shift ever so slightly against the backdrop of much more distant, seemingly stationary stars. The amount of this apparent shift, or parallax angle, allows us to calculate the star's distance using basic trigonometry. It's like drawing a giant cosmic triangle in space, with the Earth's orbital diameter as one side and the star at the opposite vertex. This method is incredibly precise for stars within a few hundred to a few thousand light years, providing the foundational, unshakable bedrock of our cosmic ladder. Missions like the European Space Agency's Hipparcos and, more recently, Gaia, have measured the parallax of billions of stars with astonishing accuracy, creating a three-dimensional map of our galactic neighborhood and giving us an unprecedented catalogue of known distances. This is the most direct and least assumption-laden method, making it the gold standard for calibrating all subsequent rungs. But parallax, for all its precision, only works for stars that are relatively close to us. Beyond a certain distance, the apparent shift becomes too infinitesimally tiny to measure, even with our most sophisticated telescopes and techniques. The stars are simply too far away for our orbital baseline to be effective. To go further, to extend our reach into the intergalactic void, we need the second rung of the ladder, Cepheid variables. These are a special, luminous kind of star that pulses, getting brighter and dimmer in a regular, predictable pattern. Imagine a cosmic lighthouse, not just flashing, but rhythmically brightening and dimming with a precise internal clock. In the early 20th century, an astronomer named Henrietta Swan Leavitt made a groundbreaking discovery while meticulously studying Cepheids in the Magellanic Clouds, two small satellite galaxies of our Milky Way. She found something incredible. The longer a Cepheid takes to complete one pulsation cycle, the brighter it actually is. This was the standard candle astronomers had been dreaming of. A direct, intrinsic relationship between a star's pulsation period and its absolute luminosity, its true brightness, regardless of how far away it appears from Earth. This period luminosity relationship often called the Leavitt Law, was a monumental breakthrough. If you observe a Cepheid pulsing every 10 days, you know exactly how bright it is at its source. By comparing that intrinsic brightness to how dim it looks from Earth, you can calculate the precise distance to the galaxy it lives in. This was the very tool Edwin Hubble used in the 1920s to discover that the universe is expanding in the first place, proving that those faint, fuzzy nebulae were not just gas clouds within our own galaxy, but entire island universes far beyond. It is the foundation of modern cosmology, allowing us to measure distances to galaxies millions of light years away, far beyond the reach of parallax. However, even Cepheids, for all their utility, have their limits. They are incredibly bright, thousands to tens of thousands of times more luminous than our Sun, but they are not bright enough to be seen individually in the most distant reaches of the universe. Their light becomes too faint to distinguish against the cosmic background, or they are obscured by intervening dust and gas. For that, to truly probe the cosmic expansion on the grandest scales, we need the third and final rung of the ladder, Type 1, a supernovae. These are the cataclysmic explosions of dying stars, and they are so incredibly bright that they can briefly outshine an entire galaxy, making them visible across billions of light years. Imagine a cosmic flashbulb burning with a consistent, blinding intensity that can be seen across the universe. These supernovae occur when a white dwarf star, the dense, burnt-out remnant of a star like our Sun, accretes matter from a companion star. As it gathers more and more mass, it eventually reaches a critical limit, the Chandrasekhar limit, at which point it becomes unstable and undergoes a thermonuclear runaway explosion, obliterating itself in a spectacular burst of light. Because this critical mass is always roughly the same, these explosions always reach roughly the same peak luminosity. They are, in essence, perfect standard bombs, or standard candles of the highest order, cosmic beacons of immense, predictable power. By using Cepheids to measure the distance to nearby galaxies that also contain Type 1, a supernovae, we can calibrate the supernovae. This means we can determine their precise intrinsic brightness with a high degree of confidence. Once calibrated, these supernovae become our ultimate cosmic yardsticks, allowing us to measure distances to the most remote corners of the observable universe. We can then observe a Type 1, a supernova, in a galaxy billions of light years away, measure its apparent brightness, and, knowing its intrinsic brightness from our Cepheid calibrations, calculate its immense distance. This is the meticulous, decades-long work that won Adam Riess and his colleagues, Saul Perlmutter and Brian Schmidt, the Nobel Prize in Physics in 2011. They climbed the ladder, rung by painstaking rung, from the closest stars measured by parallax to Cepheids in nearby galaxies, and finally to Type 1, a supernovae in the most distant galaxies, pushing the boundaries of our observable universe and revealing the accelerating expansion of the cosmos. Their meticulous measurements, refined over decades, consistently found that the universe is expanding at a rate of 73 kilometers per second per megaparsec. This number, derived from direct present-day observations of the local universe, stands in stark, undeniable contrast to the 67 kilometers per second predicted by the early universe data, setting the stage for our current cosmic crisis. For a long time, many scientists were deeply skeptical of this 73 kilometers per second per megaparsec number. They argued that the ladder was shaky, not because of the underlying physics of standard candles, but because of potential observational biases and systematic errors. They suggested that perhaps the Cepheids were being crowded by other stars in their dense galactic environments, making them appear brighter than they actually were. This stellar crowding effect, if significant, would lead to an underestimation of their true distance, and consequently, an overestimation of the expansion rate. They also raised concerns about the environments where Type 1 supernovae explode, suggesting that variations in the host galaxy's metallicity or dust content could subtly alter their peak brightness, making them less standard than assumed. These were legitimate scientific concerns, and many hoped that with better telescopes and more refined techniques, these potential errors would be identified and corrected. They thought that if we could just get a clearer view, the number 73 would gracefully drop down to 67, and the Hubble tension would vanish like a bad dream, allowing the standard model to retain its elegant consistency. This was one of the primary reasons the James Webb Space Telescope was built, to be the ultimate arbiter, the definitive check on the cosmic distance ladder, to either confirm its robustness or expose its flaws. Scientists waited with bated breath for the first results, expecting the tension to be resolved, one way or another, and for cosmic harmony to be restored. But when the data from James Webb finally arrived, it didn't lower the number. It solidified it. The telescope looked at the same Cepheids that the Hubble Space Telescope had studied for decades, but with much higher resolution and in wavelengths less affected by dust. Its infrared eyes could peer through the obscuring veils of cosmic dust and resolve individual Cepheids even in the most densely packed regions of galaxies. It did in fact see more stars. It saw the crowding that the critics had talked about and meticulously accounted for it. But here was the shock. Even after painstakingly isolating the Cepheids with unprecedented precision, even after correcting for every conceivable systematic error, the distance measurements didn't change. The number 73 remained stubbornly, defiantly the same. James Webb had looked at the blurry sign with perfect vision and confirmed that the letters were exactly what we thought they were. The error that everyone was hoping for simply didn't exist. The local measurement of 73 was not a mistake. It was a reality, confirmed by the most powerful, most precise telescope humanity has ever launched into space. This confirmation by James Webb has turned the Hubble tension into a full-blown crisis. If the measurements are correct, if both the early universe prediction of 67 and the local universe measurement of 73 are robust, then the problem must lie not with our instruments, but with our understanding of the universe itself. It means that something fundamental happened between the time the baby picture was taken and the present day, something that our standard model doesn't account for. It's as if we have a perfect map of the beginning of a journey and a perfect map of the end, but the road in between doesn't follow the path we expected. We are missing a piece of the puzzle, a fundamental law of physics that we haven't discovered yet, a cosmic variable that has subtly yet profoundly altered the expansion history of the universe. And as we continue to climb the ladder of knowledge, pushing the boundaries of our perception, we are finding that the higher we go, the more the ground beneath us seems to shift. The truth, it seems, is much more complicated than we ever imagined. The cosmic distance ladder, once a symbol of our growing understanding, has now become a stark reminder of the profound mysteries that still elude us, pointing towards a universe that is actively defying our most elegant theories and beckoning us toward a new era of cosmic discovery. When the James Webb Space Telescope was launched into the cold, dark silence of space, it carried with it the hopes of an entire generation of scientists. It was the most complex, most expensive, and most ambitious scientific instrument ever built. A marvel of engineering designed to unfold itself like a cosmic origami in the vast emptiness beyond the moon. Its primary mission was to peer back to the very beginning of time, to see the first stars and galaxies that ever flickered into existence, to witness the universe's infancy. But it also had a much more immediate and perhaps more critical task: to be the ultimate judge in the simmering dispute known as the Hubble Tension. For years, the scientific community had been divided. On one side were the early universe cosmologists, who pointed to the Planck satellite's pristine measurement of 67 kilometers per second per megaparsec. On the other side were the local universe astronomers, led by Adam Riess, who insisted on 73. The tension was a cloud hanging over the field, a nagging doubt that wouldn't go away, threatening to unravel the elegant tapestry of our cosmic understanding. Many believed that James Webb, with its superior resolution and unparalleled infrared vision, would finally clear the air. They thought it would show that the local measurements were flawed, that the stellar crowding was real, and that the number 73 would gracefully drop down to 67, bringing the universe back into harmony. Imagine you are trying to read a tiny faded inscription on a monument from a great distance through a pair of old scratched glasses. The letters are blurry, and you might misread a B for an R or an O for a Q. This was the core argument against the Hubble Space Telescope's measurements of Cepheid variables. Critics argued that because Hubble's vision was limited, especially in the visible light spectrum where dust can obscure views, it couldn't always distinguish between a single Cepheid variable and a cluster of other stars that were all huddled together in the dense galactic environments. This stellar crowding effect, they theorized, would make the Cepheid appear brighter than it actually was, because its light would be blended with that of its neighbors. An artificially brighter Cepheid would then be interpreted as being closer than it truly is, leading to an underestimation of their true distance and consequently an overestimation of the expansion rate, and thus the inflated 73 kilometers per second per megaparsec value. It was a plausible theory, a scientific lifeline, and many hoped it was the answer that would save the Standard Model. James Webb was designed to be the new pair of glasses, the high-definition, crystal-clear vision that would finally reveal the truth. Its massive 6.5-meter gold-plated mirror, operating at cryogenic temperatures, was specifically engineered to capture infrared light, which can penetrate cosmic dust clouds far more effectively than visible light. If the crowding was real, James Webb would see it. It would separate the individual stars, resolve the dense stellar populations, and give us the true brightness of the Cepheids, unadulterated by optical illusions. But when the first data from James Webb's observations of Cepheids in distant galaxies began to trickle in, the results were not what many had expected. The telescope looked at the same galaxies Hubble had studied for decades, but with its massive mirror and its advanced infrared cameras, it could see details that Hubble simply couldn't. It did, in fact, see more stars. It saw the crowding that the critics had talked about, resolving individual Cepheids even in the most densely packed regions of galaxies. But here was the shock. Even after meticulously accounting for that crowding, even after isolating the Cepheids with unprecedented precision, the distance measurements didn't change. The number 73 remained stubbornly, defiantly the same. James Webb had looked at the blurry sign with perfect vision and confirmed that the letters were exactly what we thought they were. The error that everyone was hoping for simply didn't exist. The local measurement of 73 was not a mistake. It was a reality, confirmed by the most powerful telescope humanity has ever launched. This was a moment of profound silence, followed by a ripple of unease in the world of cosmology. The judge had spoken, and the verdict was not what the prosecution had hoped for. By confirming the local expansion rate with such irrefutable precision, James Webb had effectively ruled out the possibility that the Hubble tension was just a measurement error. It had turned a tension into a full-blown crisis. If the measurements from the early universe, 67, and the measurements from the modern universe, 73, are both correct, then the problem is not with our telescopes. The problem is with our universe. Or, more accurately, the problem is with our fundamental understanding of it. It means that the standard model of cosmology, the blueprint we've been using for a century to describe the cosmos, is missing something fundamental. It's as if we have two perfect clocks, one at the beginning of a race and one at the end, and they both show different times, even though they were synchronized. It means the very nature of time and space is doing something we didn't predict, something that defies our most elegant equations. The implications of this are staggering, reaching far beyond a mere numerical discrepancy. If the expansion rate is actually 73, then the universe is expanding about 8% faster than our best theories say it should be. This might not sound like much, but it changes everything. It means the universe is younger than we thought, perhaps only 12.8 billion years old instead of 13.8 billion. A younger universe means less time for structures to form, which directly clashes with other JWST observations of mature galaxies in the early cosmos. It means that dark energy, the mysterious force that is pushing the universe apart, might not be constant. It might be changing over time, getting stronger as the universe ages, or perhaps there was a brief, intense burst of it in the very early universe, a phenomenon known as early dark energy. This would be a radical departure from our current understanding, suggesting a dynamic, evolving dark energy that our models simply don't account for. Whatever the answer is, it lies outside the boundaries of our current knowledge, demanding new physics, new particles, or even new dimensions. Furthermore, the Hubble tension is not an isolated anomaly. It is part of a growing constellation of discrepancies that are challenging the standard model, painting a picture of a universe that is consistently defying our predictions. One such example is the S8 tension, which refers to a disagreement in the clumpiness or distribution of matter in the universe. Imagine trying to predict the texture of a cake based on its ingredients and baking time. If your recipe consistently tells you it should be perfectly smooth, but every cake you bake comes out with large, uneven lumps, you have a problem. Similarly, measurements from the cosmic microwave background, our baby picture of the universe, suggest that the early universe was smoother, with less clumping of matter, than what we observe in the modern universe through gravitational lensing and galaxy surveys. Gravitational lensing, where the gravity of massive objects bends light from background galaxies, allows us to map the distribution of dark matter and visible matter. These modern observations consistently show a universe that is more clumpy than the CMB predictions allow. It's like predicting a smooth, even distribution of sand on a beach based on its initial state, but then finding large, uneven dunes everywhere. This S8 tension, alongside the Hubble tension, paints a picture of a universe that is consistently defying our predictions, not just in its expansion rate, but also in its very structure and evolution. These two tensions, the Hubble and the S8, are like two different symptoms pointing to the same underlying cosmic illness, a fundamental flaw in our current understanding of the universe. As we move forward, the focus is shifting from "is there a mistake?" to "what are we missing?" The crisis is no longer about the numbers, it's about the physics. We are entering a new era of discovery, one where we have to be willing to throw away our old maps and start from scratch. James Webb has shown us that the universe is not the simple, elegant machine we thought it was. It is a place of deep mystery, a place where the laws of physics themselves might be evolving. We are like sailors who have reached the edge of the known world and found that the ocean doesn't end. It just becomes deeper and more dangerous. The judge has failed to bring us back to the safety of our old theories, and now we are left to navigate the unknown on our own, armed with new data and a renewed sense of wonder at the cosmic enigma that surrounds us. The elegant simplicity of our model is giving way to a bewildering reality, forcing us to question everything we thought we knew about the cosmos and our place within it. The stage is set for a scientific revolution, one that promises to redefine our understanding of existence itself, and perhaps to reveal a universe far grander and more complex than any model could ever encompass. As if the Hubble tension wasn't enough to shake the foundations of cosmology, the James Webb Space Telescope has uncovered another mystery that is equally, if not more, unsettling. It has found what astronomers are calling little red dots and impossible galaxies. Imagine you are walking through a garden that you know was planted only yesterday. You expect to see tiny sprouts, perhaps a few leaves poking through the soil, maybe a few nascent buds. But instead, you find a fully grown oak tree, its branches reaching high into the sky, its trunk thick and gnarled with age, its roots deeply embedded in the earth. You know it shouldn't be there. There simply hasn't been enough time for it to grow from an acorn to such a majestic size. This is exactly what James Webb is seeing in the early universe. It is looking back to a time only 500 to 700 million Newton years after the Big Bang, a mere blink of an eye in cosmic terms, when the universe was less than 5% of its current age. And it is finding galaxies that are as massive and mature as our own Milky Way, brimming with billions of stars and complex structures. These are not the nascent, chaotic clumps of gas and dust our models predicted. They are fully formed cosmic cities, appearing in an era we once thought was too young for such sophistication. According to our standard model of cosmology, galaxies should grow slowly, patiently, over billions of years. In the early universe, matter was spread out relatively evenly, with only tiny fluctuations in density, like microscopic ripples on a cosmic pond. Over hundreds of millions of years, gravity would slowly pull gas and dark matter together to form the first small stars, which would then cluster into tiny protogalaxies. These small building blocks would then merge and accrete more matter over vast stretches of cosmic time to create the massive spiral and elliptical galaxies we see today. It's a slow, deliberate process, like building a city brick by brick, laying each foundation, constructing each wall, and adding each roof over generations, with each step taking millions of years. But James Webb is seeing cities that seem to have appeared overnight, fully formed and bustling with stellar activity. These impossible galaxies are packed with stars, many of them already old and red, indicating they formed very early and very quickly. They are far more massive and far more organized than anyone thought possible so early in the universe's history. It's as if the bricks were already there, and the city was built in a fraction of the time our theories allow, defying the very speed limits of cosmic construction. The sheer number of these mature galaxies in the early universe is also a profound puzzle. Our models predict a gradual increase in galaxy size and complexity over time, but JWST is showing us a universe that was already teeming with large, well-developed galaxies during the so-called cosmic dawn, the period when the first stars and galaxies were supposed to be just beginning to ignite. One of the most intriguing and perplexing discoveries are what astronomers have dubbed little red dots. These are tiny, extremely red objects that appear in James Webb's deepest infrared images. Their redness is key, indicating that either they are heavily obscured by dust, or they are dominated by very old red stars, or their light has been stretched significantly by the universe's expansion, meaning they are incredibly distant. At first, scientists thought they might be very distant, very old galaxies, perhaps just seen through a thick veil of dust. But when they analyzed the light from these dots, they found something even stranger. They are incredibly compact, yet they seem to contain as much mass as an entire galaxy, sometimes even more. Their extreme compactness and high mass density are particularly challenging to explain. Some researchers believe they might be baby, supermassive black holes growing at an astonishing rate, gobbling up surrounding gas and dust with an efficiency that defies our understanding of how black holes form and feed in the early universe. The sheer number and luminosity of these objects suggest a rapid and widespread formation of massive black holes, far earlier than expected, perhaps even preceding the formation of their host galaxies. Others theorize they could be a new kind of stellar population, stars that formed in a way we've never seen before, perhaps in extremely dense environments or with different initial mass functions, favoring the creation of very massive, short-lived stars that quickly evolve into red giants. Whatever their true nature, these little red dots are universe breakers. They exist in a time and a state that our current models simply cannot explain, forcing us to reconsider the entire timeline of cosmic evolution and the mechanisms that drive it. They are cosmic enigmas, challenging our assumptions about the very building blocks of the universe. The discovery of these massive early galaxies and mysterious red dots has led to a flurry of new theories, each more radical than the last, as scientists scramble to reconcile observations with theory. Some scientists suggest that dark matter might not be cold, as we've always assumed. If dark matter is warm or behaves like a wave, it might have allowed matter to clump together much faster in the early universe, acting like a cosmic accelerant for galaxy formation. This alternative dark matter could have smoothed out the small-scale density fluctuations, preventing the formation of too many small galaxies while allowing larger structures to form more rapidly. Others think that the first stars, known as population 3 stars, might have been much larger, more massive, and more efficient at creating heavy elements than modern stars, allowing galaxies to mature at an incredible speed. These supermassive first stars would have lived fast and died young, enriching the early universe with the building blocks for subsequent generations of stars and galaxies, thereby kickstarting galaxy formation much earlier than previously thought. Another hypothesis involves a more efficient process of gas, cooling, and star formation in the early universe, perhaps driven by exotic physics or different initial conditions. But these are just guesses, tantalizing possibilities that highlight the profound gaps in our current understanding. The truth is that we are seeing something that our blueprint for the universe didn't predict. The oak tree is in the garden, and we have no idea how it got there so fast, or what kind of seed it truly sprang from, or even if it's an oak tree at all. This discovery is not just a minor detail, it's a fundamental challenge to our understanding of cosmic time and the processes of structure formation. If galaxies can form this quickly, then our entire timeline of the universe might be wrong, or at least incomplete. It adds another layer of complexity to the Hubble tension. If the universe is expanding faster than we thought, and if galaxies are forming faster than we thought, then the standard model is failing on multiple fronts. It's as if we're watching a movie where the scenes are playing out of order, or where the characters are aging 10 times faster than they should, defying the very laws of narrative progression. The coherence of our cosmic story is beginning to unravel, revealing inconsistencies that demand a radical re-evaluation of our most fundamental assumptions. We are living in a universe that is not only expanding in ways we don't understand, but is also creating structure at a pace that defies our laws of physics, pushing the boundaries of what we thought was possible and forcing us to confront the possibility that our cosmic narrative is deeply flawed. The little red dots and impossible galaxies are a reminder that the universe is far more creative and far more mysterious than our mathematical models. We are like children who have just learned to count to 10, only to find that the universe is counting in a language we don't yet speak, a language filled with nuances and complexities we are only just beginning to decipher. James Webb has opened a window into a past that we thought we understood, only to show us that we were looking at a shadow of the truth, a mere silhouette against a much richer, more vibrant backdrop. The garden of the early universe is full of surprises, and as we continue to explore it, we are finding that the oak trees are just the beginning. The deeper we look, the more we realize that the universe we thought we knew is just a small part of a much larger, much stranger reality. A reality that is actively challenging our intellect and expanding the very horizons of human knowledge. These discoveries are not just data points, they are cosmic riddles, beckoning us to unravel the deeper truths of existence and forcing us to admit that the universe's early years were far more dynamic and complex than our theories ever predicted. The cosmic dawn, once imagined as a slow, gentle awakening, now appears to have been a tumultuous, rapid burst of creation. As the Hubble Tension and the discovery of impossible galaxies continue to shake the foundations of cosmology, scientists are beginning to look for a missing ingredient in our cosmic recipe. Imagine you are a chef who has been following a family recipe for generations. You know exactly how much flour, sugar, and water to add, and the result has always been a perfect loaf of bread. But one day, you follow the recipe exactly, and the bread doesn't rise. You check the oven, you check the ingredients, and everything seems fine. You realize that something must have changed in the environment. Perhaps the air is thinner or the water is different. You need to add a new secret ingredient to make the bread rise again. An ingredient that wasn't in the original cookbook, but is now essential for the desired outcome. This is exactly what cosmologists are doing now. They are looking for a secret ingredient that can explain why the universe is expanding faster than it should be, and why galaxies are forming so quickly, without breaking the elegant consistency of our observations. One of the most promising and actively researched theories is what scientists call early dark energy, EDE. In our standard model, dark energy is a constant force, a cosmological constant, that has been pushing the universe apart at a steady rate for billions of years, becoming dominant only in the later stages of cosmic evolution. But what if dark energy wasn't always constant? What if there was a burst of extra dark energy shortly after the Big Bang? A sudden, transient surge of expansion that happened before the first light was even emitted, before the cosmic microwave background was formed? This early dark energy would have acted like a cosmic kick, briefly accelerating the universe's expansion in its infancy, and then quickly decaying away. This would explain why the baby picture of the universe, the CMB, shows a slower expansion rate, reflecting the universe before this EDE burst, while the modern universe, measured by Adam Riess and his team, shows a faster one, reflecting the universe after it had been given this early boost. It's as if the universe had a sudden, intense growth spurt that our models didn't account for. A brief but powerful injection of energy that altered its entire trajectory. This elegant solution could potentially reconcile the 67 and 73, allowing both measurements to be correct within a modified framework of cosmic history. The challenge now is to find observational evidence for such a fleeting yet powerful phenomenon. Another radical possibility is that our understanding of gravity itself is incomplete. For over a century, Albert Einstein's general relativity has been the gold standard for describing how gravity works on a large scale. It has passed every test we've thrown at it, from the subtle wobble in Mercury's orbit to the spectacular detection of gravitational waves from colliding black holes. It is a theory of breathtaking beauty and predictive power, but what if gravity behaves differently over cosmic distances and across vast timescales? Some scientists are exploring modified gravity theories, which suggest that gravity might get stronger or weaker depending on the scale of the universe, or that it might be mediated by additional fields. For instance, if gravity was slightly stronger in the early universe, it could have pulled matter together faster, accelerating the formation of those impossible galaxies. Conversely, if gravity is slightly weaker now, or if there are additional forces at play, it could explain why the expansion is accelerating faster than we thought. These theories often involve adding new terms to Einstein's equations, or even proposing extra dimensions where gravity might leak in and out. It's a radical idea, a direct challenge to Einstein's legacy. But in a crisis of this magnitude, radical ideas are often the only ones that offer a path forward. It means questioning the very rules by which the cosmos plays, suggesting that our current rulebook might be missing a few crucial chapters. Then there is the enduring mystery of dark matter, the invisible scaffolding of the universe. We've always assumed that dark matter is cold, CDM, meaning it moves slowly and clumps together easily, forming the gravitational wells that allow galaxies to coalesce. This cold dark matter, CDM, is a key part of our standard model and has been incredibly successful at explaining the large-scale structure of the universe. But what if dark matter isn't so cold? What if it's warm or even fuzzy, behaving more like a wave than a particle? If dark matter particles had a slightly higher velocity, or if they had wave-like properties that prevented them from clumping too tightly on small scales, it would change the way structure forms in the universe. A warm, dark matter model, for example, could suppress the formation of very small galaxies, which might help explain some discrepancies between simulations and observations of dwarf galaxies. More exotically, fuzzy dark matter, composed of ultralight particles, could smooth out density fluctuations in the early universe, potentially allowing larger galaxies to form more rapidly by providing a different kind of gravitational environment. It would be like changing the scaffolding of the universe, allowing the building to go up in record time, or perhaps even altering the very blueprint for how those buildings are constructed. These theories are still in their infancy, but they represent a fundamental shift in how we think about the invisible 95% of the cosmos, suggesting that the dark side of the universe might hold the key to unlocking its greatest secrets. What's particularly compelling is how these proposed solutions might not just address the Hubble tension, but also the S8 tension we touched upon earlier, the discrepancy in the clumpiness of matter in the universe. A model with early dark energy, for instance, could alter the growth of structures in the early universe, potentially leading to a smoother distribution of matter that aligns better with CMB predictions, while still allowing for the observed faster expansion today. Similarly, certain modified gravity theories or alternative dark matter models could influence how matter clumps together, offering a unified solution to both the expansion rate and the structure formation puzzles. It's a testament to the interconnectedness of cosmic phenomena. A single missing piece of physics could resolve multiple, seemingly disparate anomalies. The universe, it seems, is not content with just one riddle. It presents us with a symphony of mysteries, all hinting at a deeper, underlying truth. The search for this missing ingredient is not just a mathematical exercise, it's a profound philosophical journey. It forces us to confront the possibility that our most cherished laws of physics are only approximations of a deeper, more complex reality. We are like the ancient Greeks who thought the Earth was the center of the universe, or the 19th century physicists who thought space was filled with an invisible ether that carried light waves. Each time humanity has encountered a crisis in its understanding of the cosmos, it has led to a revolution in our thinking, a paradigm shift that has expanded our horizons and redefined our place in the universe. The Hubble Tension and the Impossible Galaxies are the cracks in our current understanding that might be letting in the light of a new, more profound truth, forcing us to shed old assumptions and embrace a more nuanced, perhaps more beautiful, vision of reality. As we continue to search for the secret ingredient, we are finding that the universe is far more dynamic and far more surprising than we ever imagined. It is not a static, unchanging machine, governed by simple, immutable laws, but a living, evolving entity, constantly challenging our intellect and expanding the very boundaries of our knowledge. The recipe for the cosmos is still being written, and we are just beginning to understand the ingredients, both visible and invisible, that make up this grand cosmic stew. James Webb has shown us that the universe is not the simple, elegant place we thought it was. It is a place of deep mystery, a place where the laws of physics themselves might be evolving, or where our interpretation of those laws needs a radical overhaul. We are entering a new era of discovery, one where we have to be willing to throw away our old maps and start from scratch, guided only by the light of new data and the unwavering spirit of scientific inquiry. The search for the missing ingredient is the search for the true nature of reality itself, a quest that promises to redefine not just the cosmos, but our very understanding of what it means to exist within it. As we stand on the threshold of this new era in cosmology, we are reminded of the profound wisdom embedded in the words of the great physicist Richard Feynman. I would rather have questions that can't be answered than answers that can't be questioned. For a long time, humanity, in its relentless pursuit of understanding, thought it had many of the fundamental answers. We had the standard model, a beautifully intricate tapestry woven from the threads of the Big Bang, dark matter and dark energy. We had the cosmic distance ladder, a meticulously constructed pathway to measure the vastness of space. We felt like we were finally closing the book on the history of the universe, that the grand narrative of creation and evolution was largely understood. But the James Webb Space Telescope, with its piercing gaze into the cosmic dawn, has shown us that the book is far from finished. It has shown us that the answers we had were not endpoints, but merely the beginning of a much deeper, more profound set of questions. The Hubble Tension and the Impossible Galaxies are not just inconvenient problems to be solved. They are exhilarating invitations to explore a reality that is far more complex, far more nuanced, and ultimately far more beautiful than we ever dared to imagine. They are the universe's way of whispering to us that our current understanding, while magnificent, is still but a fleeting glimpse of a much grander truth, a truth that beckons us to look closer, to think deeper, and to question everything. Imagine you are standing on the shore of a vast, dark ocean at night. The waves crash rhythmically at your feet, a primal symphony that has played for eons, echoing the very pulse of the cosmos. You can see the light of the moon reflecting off the surface, a shimmering path stretching towards the horizon, hinting at distant, unseen lands. From this vantage point, you might think you know the ocean, You can measure its temperature, its salinity, the height and frequency of its waves. You can study the tides and chart the currents near the coast. You can even predict the coming storms. But you know, deep down, that beneath that shimmering surface, in the deep, dark abyss, there are creatures and landscapes, geological formations and ecosystems that you can't even begin to imagine. The ocean's true depth, its hidden life, its ancient secrets remain largely unknown, shrouded in an impenetrable darkness. This is our relationship with the universe. We see the stars, the galaxies, the nebulae, and the faint ancient light from the Big Bang. We can measure their distances, their speeds, their compositions. We can even map their distribution across billions of light years. But we know that 95% of the universe is made of dark matter and dark energy. Substances we can't see, can't touch, can't directly detect, and can't even begin to understand in their entirety. We are only scratching the surface of a vast, infinite unknown, a cosmic ocean whose true depths continue to elude our most advanced probes and theories. The visible universe, the part we can perceive and measure, is merely the moonlit surface of an unfathomable cosmic sea, a thin veneer over an abyss of mystery. This crisis in cosmology, therefore, is not a failure of science. It is, in its most profound sense, a triumph of curiosity and precision. It is the moment when our instruments become so exquisitely sensitive, so incredibly precise, that they can no longer be ignored, when the data speaks with an authority that transcends our preconceived notions. It is the moment when our most cherished theories are forced to confront the raw, unyielding reality of the universe itself, when the elegant mathematical constructs must yield to the undeniable truth of observation. It is a powerful reminder that we are still explorers, still pioneers, still searching for the truth in a cosmos that is far larger, far more mysterious, and far more dynamic than we are. The warning from Adam Riess, a beacon of scientific integrity, and the groundbreaking discoveries from James Webb are not a reason to despair, to feel that our knowledge is crumbling into dust. On the contrary, they are a reason to celebrate. They mean that there is still so much more to learn, so many more layers of reality to peel back, so much more to discover. They mean that the universe is not a closed book, its story already written and understood, but an open-ended epic, a grand narrative that we are just beginning to read, with countless chapters yet to unfold, each promising new wonders and new challenges to our intellect. As we look toward the future, we can expect even more surprises, even more paradigm-shifting revelations. New telescopes, both on Earth and in space, will push the boundaries of our observational capabilities even further, allowing us to peer deeper into the cosmic past and to resolve finer details of the present. New experiments delving into the fundamental nature of particles and forces will probe the very fabric of reality, searching for the elusive particles of dark matter or the subtle signatures of dark energy. And new theories, born from the crucible of current discrepancies, will continue to challenge and refine our understanding, pushing the frontiers of theoretical physics. We will continue to climb the cosmic distance ladder, rung by painstaking rung, until we reach the very edge of the observable universe, and perhaps even glimpse beyond, into realms currently beyond our comprehension. We will continue to search for the missing ingredient that can explain the Hubble tension and the impossible galaxies. that can reconcile the universe's past with its present, and its large-scale structure with its fine-grained details. And each time we find a new piece of the puzzle, each time a new insight dawns, we will realize that the puzzle is even larger, even more intricate, and even more complex than we thought. This is the enduring beauty of science. It is a never-ending journey toward a truth that is always just out of reach, a horizon that recedes as we approach it, promising endless vistas of discovery and an eternal quest for knowledge. This ongoing quest is not just about numbers and equations. It is about our place in the cosmos. It is about understanding the very nature of existence, the fundamental laws that govern reality, and the profound implications of our discoveries. The universe, in its infinite wisdom, continues to humble us, to remind us of the vastness of our ignorance, even as it rewards our persistent inquiry with glimpses of profound beauty and breathtaking complexity. The questions raised by James Webb are not just scientific, they are existential. They force us to reconsider our models of reality, to question the very assumptions upon which our understanding of the cosmos is built. What if the laws of physics are not as immutable as we once believed, but are instead emergent properties of a deeper, more fundamental reality? What if our universe is just one of many, a single bubble in a vast multiverse, each with its own unique set of physical laws? These are not idle speculations, but legitimate avenues of scientific inquiry, driven by the data that refuses to fit our preconceived notions, pushing us to expand our intellectual horizons. The universe is not merely a backdrop against which human drama unfolds. It is an active participant, a dynamic entity that constantly challenges our intellect and expands the very horizons of our imagination, inviting us to become co-creators of its unfolding story. In the end, perhaps the most important thing we've learned from the James Webb Space Telescope and from the cosmic crisis it has illuminated is a profound sense of humility coupled with an unyielding sense of wonder. We are a tiny species on a small planet, orbiting an ordinary star in a vast, indifferent cosmos. And yet, we possess the extraordinary capacity, the sheer audacity, to try to understand the entire history of time and space, to decode the universe's deepest secrets, to unravel the very fabric of reality. We have the insatiable curiosity to ask why, and the unwavering courage to follow the data wherever it leads, even if it shatters our most cherished beliefs and forces us to abandon long-held paradigms. The universe may be stranger than we can imagine, more complex than our current models can grasp, but it is also infinitely more beautiful than we can describe. A symphony of forces and particles playing out across billions of years. As we continue to gaze into the deep, dark silence of the heavens, armed with our telescopes and our theories, our minds and our imaginations, we are reminded that we are not just passive observers of the cosmos. We are an integral part of it. We are the universe trying to understand itself, a fleeting moment of consciousness in an eternal dance of matter and energy, a cosmic reflection seeking its own meaning. And that, perhaps, is the greatest mystery of all, a mystery that continues to unfold with every new discovery, inviting us to forever explore the infinite unknown, to embrace the questions and to marvel at the answers that are yet to be revealed.